Hi guys! Welcome to section 13.4 of your notes. In your notes packet, this section is the section entitled Conservation of Energy, and in your notes page, it comes just after section 13.3. There's 13.4 right there, Conservation of Energy, so this is where you'll be following along. Now, our two key ideas are how does energy change and what is the law of conservation of energy. And first, I want you to think about this situation. You give yourself and your sled gravitational potential energy when you pull your sled to the top of a snowy hill. You board your sled and you slide to the bottom of the hill, speeding up as you go. You'll remember from section 13.3 that potential energy is due to an object's change in shape or position or condition. And you'll also remember from section 13.3 that energy is a capacity to do work. So, I want you to think about this question. When, in this picture, does the sled have the most potential energy? If you guessed at the top, you would be correct. The most potential energy would be when the capacity to do work would be at its highest potential. And at the top of the hill, the sled will be able to move all the way to the bottom. So therefore it would have the highest potential energy at the top. What about the least potential energy? You're right. The least potential energy would be down here at the bottom. So, where does a sled have the most kinetic energy? You'll remember from previous chapters that kinetic energy, well actually also from chapter 13.3 again, that kinetic energy is energy actually in motion. So the sled will obviously be going the fastest when it gets down here to the bottom of the hill, and that is where it would have the most kinetic energy. Alright, let's look at this a little further. So we're asked the question, how does energy change? Oh, I thought I skipped this slide. How does energy change? Well, energy readily changes from one form to another. Here's an example. So, light energy from the sun is stored in plants through the process of photosynthesis into chemical energy. Chemical energy is then changed into mechanical energy when you eat your food and have the energy to then move forward. Electrical energy is changed to thermal energy when you cook food, and chemical energy from your gas is turned into mechanical energy when your car actually works. What I'd like you to do is draw or write an example just beside on your notes. So draw or write an example right there. Let's move on. Potential energy can become kinetic energy. Here's an example. As a roller coaster car goes down a hill, the potential energy changes into kinetic energy. At the top of the hill, it has the potential to have the capacity to do work. And at the bottom of the hill, it's doing work rather quickly because the roller coaster is moving so fast by the time you get to the bottom. Kinetic energy can become potential energy. So think about once you get to the bottom, and the roller coaster at the bottom of the hill starts carrying it up the other side. Well, as soon as the roller coaster starts gaining ground and going up the other side, its potential energy to go back down is growing, is getting bigger. So, mechanical energy can also change to other forms of energy. Think of when your car is running, it also produces thermal energy or heat. or even when you're running. Mechanical energy can change into other forms of energy, such as heat. Let's look at this graph. It says, the bar graph shown here presents data about a roller coaster car. What variables are plotted? Identify the dependent and independent variables. What does the legend tell you about this graph? Here's our graph. Let's look at it a little bit bigger. So, here's our graph nice and big. And you are asked to study the axes and the legend to determine the variables. Your first question is, blank is the variable on the x-axis. Two variables are plotted on the y-axis, blank and blank energy. So, first we need to look at that graph and determine where the x and y-axis are. A lot of you are way ahead of me and have already guessed it. So, down here is my x-axis, which as you can see is location. And then over here is my y-axis. And you can see that that is total mechanical energy, but because you have two blanks there, we actually need to look, and I should write it this way, y. Now it's upside, and now it's right way up. Now we need to look down here at the key. So at the key, we can see kinetic energy is in blue, and potential energy is in purple. So kinetic and potential energy are on the axes of the graph. So they are our variables. Now number 2 says, consider the relationship between the variables. The independent variable is location, which is down here, because the cars blank and blank change with location. Okay, well I guess, yeah, yours does say that, because the cars blank and blank change with location. Well, what changes with the location of the car? From here to location C, what's changing? Well, it's your kinetic and potential energy again. Now number 3 states, examine the legend and how it relates to the graph. Well, according to the graph, this side is just total mechanical energy. The legend explains for you that mechanical energy is actually made of two things. It's made of both kinetic and potential energy. If we were talking about a real roller coaster, just like in the sled illustration, where would this roller coaster be at the top of the hill? Would it be at position A, B, C, or D? Well, for those of you who said position A, you would be correct, because at A, there's the most potential energy. So we know that A has to be at the top of the hill. I would like for you to write this label on top of your graph in your notes. Position A would be at the top of the hill. In your notes, it's actually really hard to see the difference between kinetic and potential energy. So I think that a good idea would be to use a crayon or a highlighter or even a pencil to illustrate which is which on the graphs in your copy, since yours didn't print in color. Now, if A is at the top, B would have to be slightly after the top of the hill. And according to our sled example, where do you think the roller coaster has the most kinetic energy? You would be correct if you said the bottom of the hill. And finally, the last position would be as the kinetic energy is turning back into potential energy and starting to carry the roller coaster up the other side. Now, I realized after I printed this that I actually forgot to print the back page of the lab. And so there's a couple things that I would like for you to define for me down here at the bottom. So I forgot to print it, and you can see the first thing I want you to define at the bottom is the law of conservation of energy. Once you flip it over to the back side, I would like you to define the first law of thermodynamics. You can find those in your book in section 13.4. Finally, I want to talk about different kinds of systems.
The part?
Okay, so this is the last thing I want you to put in your notes. An open system is when energy and matter are exchanged with the surroundings. A closed system is where energy but not matter is exchanged. And an isolated system is where neither energy nor matter is exchanged. When you defined on your notes what the law of conservation of energy was, you would have learned that energy can't be created or destroyed, and the amount of energy in the universe never changes. It just goes from one form to another. You would have also found that the first law of thermodynamics stated that for any system, the net change in energy is equal to the energy transferred as work and heat. In light of this, it makes sense that in an isolated system, nothing can escape. Neither heat nor energy is exchanged. In a closed system, energy can move in and out. It's like when you hold a styrofoam cup with a lid on it. Actually, here I have a picture to illustrate this. Okay, so an open system, matter can move, energy can move. You can look at this beaker. Water vapor might come out the top. So even though the law of thermodynamics says that there's no net change in energy, it's just transferred into work or heat, we can't record it very well in an open system because we can't be accounting for where all the matter went or how much matter left very easily. Now, in a closed system, we can always make sure that the amount of matter we start with at the beginning of an experiment is the same as the amount of matter at the end because it's corked and no matter can escape. But heat can escape, or energy, to the outside environment. Now, if we have a completely isolated system, we can prove the law of thermodynamics because in a completely isolated system, energy can't get out and matter can't get out either. And we would find out that no matter what experiment we do, the amount of energy would be the same both before and after the experiment, and the amount of matter would be the same both before and after the experiment. So once you get those definitions in your notes, open system, closed system, and isolated system, you are done with this section of notes. Congratulations and good job.